Continue now through various access schemes that we have in satellite networks. We talked about FDMA. Now we're going to talk about TDMA. TDMA is time division multiple access. It assumes that the users are sharing the transponder resources one at a time. Right? No two signals exist at the same time, but instead each user uses the entire transponder for a certain duration of the time. That's kind of illustrated here. Just like in every other TDMA system, you take the t-axis, the time axis, you segment it into portions that are usually referred to as time slots, and then allocate those time slots to individual users. Like in this case, the first you have the user, the Earth Station 1 communicating, then it completely ceases communication, then Earth Station 2, Earth Station 3, then it loops around to Earth Station 1 and Earth Station 2 and so on. So these guys have intermittent transmissions. Well, if you look at what comes back from the repeater, from the satellite, is essentially all of these signals concatenated in time. Now, there are some good sides to it, some bad sides to this access. The good side is the TDMA is I would say, natural extension of the TDM multiplex that you have on the ground. Most of our long-haul communication in both data and voice is time division multiplex over fibers and so on. So TDMA is actually a logical extension of the communication scheme, and in some ways it's the most easiest one to implement. Now, there are some bad sides. The signals are wideband, right? Because you have a transponder, and you give this whole transponder to a satellite, to an Earth station, whether it actually needs it or not, right? Sometimes you may have a user that has a very low data rate, but you give a very large bandwidth. So what that does, it makes all the transmit power on the ground always big, right? And we're going to go through that to a specific example that illustrates that fact. So TDMA access is really, I would say, accommodating when you're backhauling a large amount of data. If you're having huge, let's say, backhaul Earth stations that are carrying, let's say, a large amount of traffic, then it's appropriate to go TDMA. If you have onesie, twosie users with a relatively low bandwidth, then this becomes inefficient. And we're going to talk more in detail about that through an example. This is a little bit more detail of how this is done. The communication here, you have to think about time in time slots, right? So you have time slots allocating. One cycle through allocation of these time slots makes a time frame. So if you look at Earth Station 1 being allocated time slot, when the Earth Station 1 comes on its next turn, the time in between those two is called time frame. And usually have n time slots in a time frame. If you allow n Earth stations to be in the access, then n time slots would constitute time frame. Now, that's how the time is divided. And you can have upper level of organizations of these time frames, like sometimes the certain number of frames would generate super frame and then hyper frame and higher level of organization. But essentially at the time scale, you're talking slots and frames. Now, within one slot, the base station, the Earth station would send certain amount of data. Now, that data that is being sent within one time slot is referred to as a burst. The TDMA transmission is bursted transmission. You burst the data, and then you wait until its next turn, you burst again, and you wait until it's your turn again, and you burst. So you communicate in burst. And this is the typical burst structure here. Burst, you would always have two sections, right? One would be what is called overhead. And we'll talk about what does overhead have to contain. And the other one is the user data. So if you look at this example here, so this would be like a burst that comes from one user. This is the burst that comes from user one of them. It will contain the overhead information, which we would refer to here as a preamble. And then within this data, there will be portion of it that goes to other users in the system. So here you have a section that goes to A, the section that goes to B, and the section that goes to C, right? So that's, and then if you look at, so you would have all of your data multiplexed, you know, that comes from different data streams. It would be time division multiplexed, buffered here, and when it's your time to transmit to a satellite, you would aggregate this into burst and send this to a transponder, and the transponder would embed that in your proper time slot along with all the other data that it gets from all the other Earth stations. All of these data are transported down to the ground. Each one of these Earth stations on the receive side would demodulate all of it and then just discard everything that's not going to it. So you have here Earth station D sending this burst. Portion of it goes to A, portion of it goes to B, portion of it goes to C. Each one of them will demodulate all of it, but just keep the data that is pertinent to its users, right? What needs to be demodulated. Now, since you have all of this data streaming from various locations, there is a need for rate adjustment, and that means that, you know, aggregate sum of all of these data rates coming in has to be equal to the data rate coming out. So that means if these are the streams, let's say, I don't know, 64 kilobits per second, then the overall data rate on this link has to be much higher, right? Because it cannot accumulate the data here. Everything that comes in has to come out, kind of like a version of a KCL, if you remember second theory, right? This is the structure of a TDMA burst. This is an example of it. This is used in Intelsat satellites, and this kind of illustrates what we have within one burst. So, just how is this laid out? You have this is just see here. This is here the preamble. Then you have guard time, and then you have a traffic burst. The preamble contains the overhead information, and there are several things that preamble has to contain. Now, before I go into details, here's the big picture here. You have TDMA is very sensitive to time, right? Because everything needs to be aligned in time. And on the ground, that's not a terribly difficult task. But even on the ground, we have to do certain processes to make sure that happens. Over large distances that we are trying to communicate here, the alignment is really critical, because all the timing tolerances that you have are relatively small compared to the large propagation delays that you encounter. If you're talking to a geostationary satellite, you're talking 250 milliseconds of the round trip time. If you're now trying to, on these 200 milliseconds, tolerate few microseconds, you're already talking about very fine tolerances relative to the overall delays in the system. So you have to have something that makes sure that all of these clocks beat to the same heartbeat. And the only way to do that is to do that adaptively, to make sure that as the system is operating, that it constantly recalibrates itself. You cannot hope that you're going to set the timing once and let it run for a long time without being recalibrated. So you have to kind of all the time acquire timing references. When you try to demodulate the traffic data, before demodulate the burst, there are several levels of synchronization that you need to acquire. First, you have to acquire what is called carrier synchronization. You have to sync up your receiver to the incoming frequency and incoming phase of the signal that you're trying to demodulate. Now, there is a drift in frequency. There's also, if you're talking to MEO or LEO satellites, there's also Doppler shift that you have to take into account. But in any instance, there's always going to be phase, a line Q component that you need to recover. So that's the first one. And this, in the burst, there's a certain number of bits up front that are either just zeros or just ones, right? Unmodulated carrier that you're going to try to synchronize with. Use what is called phase lock loops to discover the phase and lock to the frequency of the incoming signal. Now, once you synchronize to the carrier, then you have to understand which burst are you really talking to, right? Because if you think about it, there's a whole bunch of bursts coming in their respective time slots, and you want to listen to a particular one. So to do that, you have to actually decode which Earth station you're listening to. And this is done through what is called unique word. Or in other words, you would assign an identifier to a base station, which is usually some specific code. So when you decode that code, you know which Earth station you are listening to. But it goes more than that. This codes that is referred to here as a unique word is a special kind of code that allows you to detect the beginning and end of your symbols. Do your symbol synchronization. Remember, when you synchronize to carrier, all you did is detect the frequency and the phase of the INQ components. But there are multitude of phase or many periods of your carrier frequency within a duration of symbol. For the operation of the matched filter, you have to know where the beginning of the symbol is, where you're going to start integrating, and where the end of the symbol is, where you're going to start making a decision what symbol has been sent. To detect the beginning and the end of the symbol, you have to find where those boundaries are. And the way how we do that, we send these unique words that will allow us to internal autocorrelation determine the beginning and the end of the word. Now, there's one thing that is subtle here. Unique word also helps you resolve what is referred to as carrier ambiguity, right? You can synchronize to the two carriers, but which one is I, which one is Q, right? So by detecting this unique word, you're actually resolving which one is which. But the big point is going through this overhead. By this time, you're actually able to read data, right? So you do the carrier synchronization, bit synchronization, resolve the phase ambiguity, and you start reading the data. There is some overhead data that is built into this burst. This is an example. It may be different from system to system. But in this system, we have TTY, usually stands for teletype. So if I want to send an SMS to a guy sitting in a different Earth station, I can use that just using this teletype channel. SC is a service channel that is there to accommodate signaling that goes between the different Earth stations in the access. And voice over wire allows you to talk to other people that are in this network, all for the purpose of managing the network. Usually, when you talk TDMA, you're talking big backhaul dishes that are carrying a large amount of traffic, and they're usually manned Earth stations. There are people sitting there watching this traffic and making sure everything works correctly. So there's always certain percentage that is allocated to facilitate their communication, either automatic between different devices in the network or between the people that are servicing the network. And then you have, in this particular case, the rest of the burst is filled in with the traffic data. In this particular example, it is assumed that it's carrying n times 64 kilobit per second channels, right? So you're carrying n voice channels in this network. So this burst is given for voice communication. There's a CDC here field. CDC stands for not Center for Disease, but it's cyclic check, right? So it's a CDC. Oh no, this is control and delay channel. Contains the delay information for synchronization. Okay, I'll talk about it in just a second. But this is a channel that allows you in initial time to synchronize to the framing of the TDMA. So in a nutshell, this is your frame. Frame contains bursts. Burst contains two sections. One is the overhead and the other one is the data. overhead has to have some physical overhead that allows the receiver to actually properly synchronize to the burst, has to have some signaling overhead that allows you to communicate between managing entities of that network, and then there's a user data. And then the efficiency of this whole scheme is however much time you give for a time slot minus the overhead, it gives you what is left for individual users. Now, out of this time, if this is overhead, then the users pay only for this portion, and the cost of this needs to be absorbed somehow. Okay, so let me see what just reiterating what I just said, burst reception. Every station would receive all the bursts, and then it will actually demultiplex them and then utilize whatever is intended for its own users, right? And then you can generate multiple streams going in different directions. I think this one, at least initially, it's very simple. Okay, so this goes to efficiency. So when it comes to a TDMA systems, one of the major characteristics of a TDMA system is its efficiency. Let's define an efficiency in a TDMA system. So here is an example of a frame. So from here to here is the frame. And then you have a whole bunch of bursts here. Usually there is, in the TDMA systems, there is concept of a master and slave. Master one is the ear station that will be providing timing for everybody else. Everybody else might be coming in and out depending on the traffic, but master always transmits. And the master transmits what usually just reference burst that contains nothing but overhead data that allows everybody else to synchronize to the timing structure of this frame. Now the rest of them, they have all of these bursts. Each burst would contain preamble and a date. Let me ask you this, why does every burst need to contain preamble? Why can't you just synchronize to a carrier and bit based on master and just discard the preambles from all the others? Yeah, not only that, they come from different places, right? They're coming from different places on the ground. They all meet at the transponder, but at the transponder, even though you may make an attempt to synchronize them on the ground, by the time they reach the transponder, they're completely random relative to their phase and even to their frequency, because there's a drift among different earth stations. There may be Doppler shift. So there are many reasons why you have to have this burst containing its own preamble, because that preamble traveled the same path as the data. Therefore, it contains all the information that you need to sync to demodulate the data itself. So to calculate the efficiency, you calculate the data time. The data time is whatever is the duration of the frame minus the length of the preambles and the length of the guard times that you have, right? These are the times that you're not using. If you have n stations in the axis, then you have n durations of the preamble and n durations of the guard time. And then total available rate for all users is whatever is this one divided by the frame, what percentage of frame you're actually transmitting data, times the physical layers data rate that this transponder supports, right? If you're communicating at 120 megabits per second, but you're communicating 90% of the time between the user, then 90% of that 120 megabit is your actual data rate available to the user. And if you want to rate for individual user, then it's this, I guess, whatever is the time allocated to the individual user minus its preamble, its guard time, times the total rate divided by the frame. So this is the portion of the time that you're communicating to a given user, and they claim a specific portion of the total rate. The TDMA efficiency is defined as this. It's defined as the ratio of the time that you that you're sending the actual user data divided by the total time that is allocated to a given frame, right? What percentage of the frame you're actually sending the data? Now, we defined this before. We looked at what the TDMA efficiency was in terrestrial systems, and I don't know if you remember example, but this was very low, right? We're talking sub 50% when you take into account coding and all the time that you need to waste on equalizing and all these other things because the channel is very non-favor. Here, it is not uncommon to have efficiency 90% or even 95%. So we have a very good efficiency for two reasons. First, we are talking big earth stations with lots of power, so the link margins are good. You're always communicating with a good signal-to-noise ratio, and therefore, you don't have to use very sophisticated coding, right? You don't have to use like turbo codes or convolutional codes that we use in terrestrial networks. The second reason is the channel is much better. We don't have relay fading to deal with here, right? Once your channel is very much like AWGN, so once you're operating at a handsome, sufficient signal-to-noise ratio, then you don't have to do much of the coding and you don't have to have much of an overhead. So the only overhead is this overhead that you have to have for synchronization and then signaling overhead that makes the earth station function and improve.
Sir, did you say that we don't have any coding techniques in this?
We always have some coding, but it's much lighter, right? We would usually here, restrict ourselves to error detection coding or some
FEC always exists, I think. FEC.
FEC, but not as high. Like for example, if you think about some of the coding that we use in terrestrial networks, we use 1/3 convolutional encoding. So that means for every bit that you send, information bit, you have 3 bits that you're sending. So for every 1 bit that you send, 2 of them are there to protect that 1 bit, right? Because the channel is so hostile, right? Here, it's never like that. You would add cyclic redundancy check or something that will allow you to detect and discard, erroneous data, right? But you wouldn't go with convolutional encoding or anything that is that heavy, right? Especially not for the large backhaul TDMA satellites. You may do for LEO when you talk directly phone, right? But that's a different story, right? Here the coding is much lighter because the channel is much more easier to deal with than the relay fading channel that we have in terrestrial networks. So here's an example. Let's I don't know if I've done it here or I just read it. Okay, so here's an example. So it says, consider a satellite with the following parameters. Strain duration 2 milliseconds, preamble for reference station 477, and preamble for other Earth station 463, and guard time this long, and then you have 2 reference bursts per frame, and cellular rate of 120 megabits per second. So let's distill all of this into an example of how does this frame look like. This is a t-axis. This is the duration of the frame, and we say that from here to here we have 2 milliseconds. That's the duration of the frame. It says it has preamble for reference station 477, and there are 2 reference bursts per frame. These are there these are your heartbeats. These are the ones that synchronize everybody to the system. It says that there are 2 of these guys, and the one is presumably at the beginning, and the other one is in the middle of the frame. So these are your 2 reference bursts. Each one of them is 477 microseconds. And then you have guard times of 1.06 microseconds. So there's a guard time here, T guard, T reference. And then there are all of these bursts that are that are allocated to individual transmissions. Each verse has its own preamble that is 4 times 4.63 microseconds, and then the rest of it is dedicated to the date, right? The length of the guard time is 1.06 microseconds. The questions are here: determine the rate to individual user. Rate to individual user. Well, let's first determine the overhead for this whole system. So the time dedicated to overhead would be 2 times 4.77 microseconds. That's the time that for these two verse here. Then you have n times 4.63 microseconds, and then plus n plus 2 times 1.06 microseconds. Why n plus 2? Because you have n plus 2 guard times, right? Even after these reference bursts, you have a guard time, right? So this n plus 2 guard times, n plus 2 preambles as well, but they're of a different length. You have n preambles of this length and 2 preambles of this length. So the T data will be your T frame minus your T overhead, and then our total becomes T data divided by T frame times R at the physical rate, right? This satellite supports 120 megabits per second at the physical layer, but not all. It's not communicating all the time. There are all of these overhead things that reduces this data. So when you do the calculations here, and for some reason I assume n equal 10. Why do I say 10? Oh,
10.
does it say?
Shared by 10.
Okay, all right. So if I assume n equal 10, then this is what calculation gives you. T overhead is 68.56 microseconds. And then total rate, RT, available to all the users becomes 2,000 microseconds minus the overhead, which is 68.56 microseconds, divided by 2,000 microseconds, and then times this 120 megabits per second, and this gives you this rate of 115.89 megabits per second. But that data rate is for all the users, so it needs to be shared between 10 of them. So per user, you get data rate. Our user is your total rate divided by n, which is this 11.589 megabits per second. That's on the transmission side. And the efficiency of your TV main, so this would be C, efficiency. Nu becomes your TD over T frame, which is your T frame minus your T overhead over T frame. In our case, this becomes 2,000 microseconds minus 68.56 microseconds, everything divided by 2,000 microseconds, and this gives you efficiency of 96.6%. So very high efficiency, as it is common in satellite, right? Not like their terrestrial counterparts. All right. So let's look at a little bit more into synchronization, right? And this is, again, going back to that, what I would like to do is, I'll review a little bit what I just said, and then we'll talk about how you actually join the TDMA network. How do you acquire these kind of synchronization? Let me just say that before we go. There are two types of synchronization that we need to worry about. One type is you at the receiver, you're listening, so an incoming burst. So you have to synchronize to the incoming burst so that you can demodulate the data that are coming from that incoming burst. And that's the synchronization that I already talked about. Synchronization to the frequency and the phase of the incoming carrier, and then synchronization to the symbols so that you can have a proper operation of your match filter. So that's synchronization on the reception side. There's another synchronization that we need to worry about, is the synchronization on the transmission side. Now, when you're transmitting, you have to be very cognizant of when to transmit, so that you make sure that you're not stepping over somebody else, right? It's very easy to step over somebody else here if you have an inaccurate estimate of timing because of all of these large delays that you're dealing with, right? So even a fraction of a wrong estimate might put you over in the next time slot where you have two bursts colliding and pretty much none of them is being received. So we'll talk about both of them. But this is an example, as I said, of the preamble. There are several synchronization levels. First one is the carrier recovery, and this is these bits here that I have that allow you to synchronize to the frequency and the phase of the carrier. Then symbol synchronization, you use the unique word for that. Then once you have the unique word, then the unique word serves the two purposes. It will help you delineate the symbols, but it will also be, that's why it's called unique word. It will also carry a signature of a particular earth station. So the earth station will get a unique word that will identify to the receiver on the ground. So if I'm directed to listen to that earth station, then as I demodulate the burst, I'm going to be looking the burst where the unique word is of a proper number or whatever is the scheme that I use. And then once you know the unique word and you synchronize to the earth station, then you actually have to know where the beginning and the end of the frame is so that you can go to appropriate time slot within every frame and listen to the transmission that you're trying to do. These are all the steps that you have to go when you're trying to receive the TDMA reception. So let me talk a little bit more about unique word. What is a unique word? Unique word is usually a code that has noise-like autocorrelation properties. Now we've seen these kind of codes before. What kind of codes are we talking about?
Yeah.
For example, PN codes, right? So why is PN code particularly suited for this? Because if I have a PN sequence, right, then I can be actually at the receiver side sliding the same sequence until I find the proper match, the highest autocorrelation. If I do that, then I know that if I position my timing relative to this maximum autocorrelation, and I know how many bits I have in my PN sequence, I can divide this time into bit intervals. And this gives me the length of my, not necessarily, the length of a symbol, right? The symbol intervals. And that helps me understand, okay, this is where the symbol starts, this is where the symbol ends. And this will allow me to correlate the rest of the sequence through the mesh filter and sample at the proper time to do the correlation. So PN sequences are commonly used in unique words, as a matter of fact, almost all the time. And there's yet another beautiful property of the PN sequence. If you have a PN sequence of the length m, how many unique words can you generate? Well, m minus 1 unique word, right? Because every shift of that sequence becomes orthogonal to all the other shifts of that sequence. That's one of the beautiful property of the PN sequence. So what that does is it allows you to use the same PN sequence and have n-1 different codes that you can now assign to different Earth stations. So, and have the same correlator that would actually go through the cycles and be able to identify different Earth station as in the same step as it is identifying the symbol by symbol time. So PN sequences are quite popular here. I'll go through this in more detail next class because we're going to be talking about CDMA, and these sequences are used in full division multiple axis as well in a very similar fashion. Okay. All right. So that completes the synchronization at the receiver side, right? The receiver receives these bursts. It needs to synchronize to the incoming signal so that it can be modulated properly. The question now is that we're going to be talking about now is synchronization between different Earth stations. What is happening? You have the frames, and they're divided into time slots. But where is the reception for all of these signals? It's way up in the sky. You have all of these transmissions that are coming from the ground. They have to be synchronized in such a fashion so that every single burst falls within its own time slot. If it doesn't fall within its time slot, it might actually come into adjacent time slot either before or after. And what happens as a result of that is collision between the bursts, and that pretty much means that both of these bursts are going to be lost, right? So how do we maintain this synchronization? Well, this is an illustration here, and let me spend a little bit of time here trying to explain what is going on. There is this burst B0, and that's a burst of a reference Earth station, right? In the TDMA, I already mentioned there's going to be one Earth station that is considered master Earth station. This Earth station will always be active, and it will provide, if nothing else, just a reference burst so that we all know when the beginning of the frame is. Now let's say my Earth station tries to join the network. Then let's say I'm trying to join the network in nth time slot, right? If I know the beginning of the frame, it's easy for me to calculate how much do I need to delay after the beginning of the frame to fall within a proper time slot. So if I can determine when do I need to transmit so that I fall within the first time slot, then I can easily delay by increment of integer multiples of the time slot durations to fall within a particular time slot. So how do I estimate when do I need to transmit to so that I reach the transponder within the first time slot? Here's the process that the Earth station would go through. It would listen, and it will detect when does it see the reference frame, and we're going to call that time start of a reference frame, right? Then it will say, okay, well, I have a rough estimate how far I am from the satellite, right? That is for geostationary satellite that can be easily determined. Even for LEO satellites, we can actually get that estimate relatively easy. So you can say, okay, well, I'm going to delay by that approximate number, and this is what I will need to transmit so that so that my burst would fall within this first time slot. And then on the top of that, I'm going to delay by dn. That's the n times the duration of the time slot. And then if I transmit here, I'm going to fall within an appropriate slot. The weak part here is my estimate of dn, right? That's a ballpark estimate. So at this point, I cannot be that courageous to just transmit with a full burst. What I'm going to do is I'm going to transmit my just my preamble, right? I'm just going to transmit the preamble and leave the data out for now, right? This is what sometimes is referred to as shortened burst, right? I just send a preamble. It can be the regular preamble, or it can be slightly longer preamble that allows you to do better synchronization, but nevertheless, it's the burst not within its full duration, right? So that you're assured that you're not going to spill into adjacent time slots. When the satellite receives this burst, it will echo it back, right? Because satellite just repeats the whole signal and sends it back. You know where this burst was supposed to arrive. You're going to now listen to your time slot and see where in the time slot did this burst actually arrive. And if it was delayed relative to when you thought it should be, then you need to advance your transmission. If it was advanced relative than what you thought it should be, you're going to delay your transmission to align this burst with a time slot. Did you follow the process? So that way you're going to refine this first estimate of dn, right? And that way you can join the network. And if you approach it that way, then you can have a flexible number of earth stations that are joining the network. They don't have to be active all the time. They can join when they need to transmit certain traffic. Right? And then once they all join the network, then you end up with this kind of situation where you have all of them, being delayed by their corresponding times with their estimates of capital Dn, and then they're all falling back within their corresponding time slot. Now, if you look at, go ahead.
So, but how do the S stations tell what time slots are actually free? If the S stations are talking to the satellite, how do they know where to actually send the data to?
Well, remember, the satellite transponder is just a repeater, right? So you're actually receiving everything. You're receiving the signal. So you see right away which time slots have channels or not. So that's one way. You can actually receive the signal and see which one are occupied. But that would be you kind of running a danger if you have in a particular spot low signal to noise ratio. You may overstep, right? Not realize that's the case. There is no standards here. Unlike terrestrial communication systems, where everything is standardized and you have broadcast channel that would inform the users on such things, here it's kind of on a case-by-case basis. So you can rely, if it works on your application, on just listening, or you can actually have an overhead channel that would broadcast which time slots are free. But a lot of these networks are actually set up manually, right? Where you have a network of a high-powered earth station that you bring up manually, and you say, you guys use this, you use this time slot, you use that time slot, because this is all in a backhaul. Remember, TDMA is usually used for large earth stations that are sending a lot of data. So you set this all up and then you just operate the network. Dynamic access is not very common here.
Professor, are these delays constant? So once you send the preamble, then now you know the delay, so you can send the data. But then this delay might be time varying, right?
The delay might be time varying, and that's why I wanted to go back and show you something that I skipped earlier. So, let me show you that. I think it was in lecture 17. I said I was going to go back to. I don't know if you can see this. CDC, control and delay channel, contains the delay information for synchronizing the transmit bursts, right? So there is a constant feedback that goes through this channel on where does the preamble actually arrive within within the allocated time slot, right? And that allows you to recalibrate on an ongoing basis. everything here when it comes to timing needs to be adapted, right? Because there's so many different clocks, and they're all at different locations that if you let them run unsupervised or without any feedback, then they're all going to start drifting from one another. So here you have to actually recalibrate all the time.
So how often are these short bursts sent? So you probably have like...
Hopefully they're not sent, they're sent only when you're acquiring, right? Because you're not drifting all of a sudden, you drift slowly, right? So as you drift, as you keep on receiving signal, then you say, okay, well, this drifted, that's why you have these guard periods. Your signal starts drifting, and then you say, oh, okay, there is a drift of so much, so advance it, right? So you're kind of always kind of wobbling and then issuing commands that advance transmission to stay within a given frame. You never allow it to drift outside of the guard period, right? That would be excessive, right? And these guard periods are now varied, depending whether you have mobility. If you have LEO satellites where you have to deal with a lot of mobility and variation in distances, then you set your guard periods to be larger. If it's a stationary, geostationary satellite that with a fixed network on the ground, and once you calibrate it, then it doesn't drift much. But nevertheless, it always drifts. So you have to have this closed loop, as it's called, to constantly calibrate your time.
So, sir, that looks exactly like the broadcasting channel in cellular communications.
It's the same purpose, right? It's the
Yeah.
same purpose. If you remember, in a personal communication system, we call this time advance.
Right.
And if you look at in GSM, you have ability to advance, up to 64 symbols.
Time advance or time offset?
Time advance, because you're compensating for delay. So if you're really close to the base station, then you don't have to advance your timing. You're going to be
Right.
within your burst. But then if you start moving away, the further, every 512 meters, you have to advance by one symbol to make sure you fall within your time slot, right? So it's the same, exactly the same concept.
A different name.
But different name, and it's particularly hard here, right? Because I will point that out. When you estimate GSM or terrestrial systems, you're usually estimating over a single frame, right? Here, if you look at the duration of time over which you're doing estimates. I don't know if it's in this time here. It says MTF. How large is M? Well, what did our example say just a couple of slides ago? It says, let's assume the time frame of 2 milliseconds. So duration of the time frame is 2 milliseconds. What is the duration of Rn over C? Rn is the distance to the satellite divided by the speed of light. It can be 100 and something milliseconds, right? So this n is several, even 100 frames further down the line, right? So you're estimating over many frames, right? The delay here is large, right? So the estimate becomes harder to achieve. So, but the concept is the same, exactly the same. You have to make sure that your transmission is aligned at the reception point, right? Because where all of these signals meet, it's the transmission many to one. All of them meet at the transponder. They shouldn't be stepping one over the other. Right? So that's one concept. It's called closed loop. Why is it called closed loop? Because you're having this feedback that goes back and forth. You're actually adjusting your transmission based on an echo from the satellites. Now there is a different paradigm. This one is an open loop transmission, and this one is appropriate in a slightly different scenario where you have these are big data station, and you have a local that are talking to many low data rate endpoints. Right here, you have many low data rate stations that may join or leave the network, and then you have 3 big stations that are communicating to these guys in some sort of data delivery. This may be, for example, individual internet users that are accessing the internet hubs, or maybe something of those like. These are sort of hub earth station, and these are individual low data rate users. Here, it is not practical to do this kind of ranging, so we do something that's called open loop. How does the open loop work? Where here, if I can, here you have these 3 guys sending the data and then receiving the same data as they sent, right? These guys are at the known locations on the globe, right? Let's say you have 3 earth stations throughout the United States. One is in the East Coast, West Coast, and one in Florida, or let's say in Texas. They're all going to send the data to the satellite, and then they're all going to receive the data from the satellite. Now, they're going to send the sequences that will allow each earth station to precisely range how far this earth station is to the satellite. Based on this data, they can triangulate the position of the satellite, right, in 3 dimensions, right? And they can broadcast the data. So you can say exactly, this satellite is located at this point in space. And this information is now available to every one of these local users, so they don't have to do ranging. They know exactly their location, and they know how far they're from the satellite, so their estimate of the distance is much more accurate. Right? In this case, you can join the network much easier. Right? You can just send a burst and be much more reasonably assured that you're going to fall within your time slot. Right? This is what's called open loop, and it's slightly different model because here you have big hubs that are talking to a smaller, larger number of low data rate users. So this is called open loop. So these are the 2 synchronization. Just to summarize, we have a synchronization of the incoming signal that's done at the receiver, and then synchronization to the network, which is access synchronization that's done at the transmitter. The transmitter needs to be synchronized to the frame structure of the TDMA so that it makes sure that it doesn't overstep on all the other transmissions that are happening in the network. Earlier, I mentioned that TDMA is appropriate for high-powered earth station, for the high data rate. Why is that the case? Think about it this way. Every time you're allowed to transmit, you're given the entire transponder. If the transponder is having a large bandwidth, which they usually do, let's say 30 or 50 or 70 megahertz, that kind of dictates that you transmit at a very high data rate. Now, when you say, I'm going to transmit at a high data rate, and to make sure that this data goes through, then that means that you have to transmit at a relatively high power, right? Just to maintain the power spectral density, because your channel is wide, and then you have to actually, to maintain the signal to noise ratio, that means you have to provide quite a bit of power, right? And even though your transmission now is short, because you don't have much to send, you still have to do quite a bit of power. And for that reason, as I said, these guys require quite a bit of power, and they're appropriate for backhaul stations. Let's just work an example here. This is the example 632 that calculates what this power is and compares what that power would be in the case of the FDMA access. And you can see that even though for many applications here on the ground, we have abandoned FDMA, right? Because as a legacy scheme and not very efficient, it's still surviving in satellite because it allows you to use smaller portion of the bandwidth, and therefore it allows you to transmit much smaller power. Right? And a lot of times we are power limited in satellite communications, therefore FDMA is appropriate because it tells you, if you don't have much data, then your power is relatively small and your utilization of the bandwidth is relatively small. So let me go through, this is an example. Example 6.3.2 in the textbook. Let me just do one more thing. Let me see what does it say. Okay. So this is the end of this. So let me turn this back off. And then I have much more going on board. It says consider BSET Earth station. So BSET BSET is an acronym that stands for very small aperture terminals. What that implies is that your antennas are small, right? And usually VSAT systems, they operate at higher frequencies, where even with the smaller antennas, you can achieve considerable gain. Nevertheless, the antennas are small, which implicates that you have link budget disadvantage, right? And that translates into relatively low data rates that you can support with these kind of systems. So the VSAT in the US, which is part of a TDMA network, using the bandwidth of the transponder is 54 megahertz. And it is operating on a domestic KU geostationary set. So you have a lot of these Earth stations. They're utilizing 54 megahertz transponder that's in a KU band on a geostationary set. The VSAT Earth station has a 1 meter antenna, so the diameter of the antenna is 1 meter. That transmits 64 kilobits, so the rate per user is 64 kilobits per second. And it uses QPSK transmission. Modulation, the rate at the physical rate at the satellite is 30 megabits per second. See, the transponder that is 54 megahertz per second, if you want to use it in a TDMA mode, that means you're assigning the entire 54 megabits. You don't want such a low rate. You have to actually use the rate that is somewhat in the relationship to the bandwidth of the satellite. In this case, the physical rate is 30 megabits per second, and then C to N on the uplink is given as 20 dB. Calculate required transmit power if the following are known. So calculate EX power if one knows all of these link budget parameters. So gain of the Earth station antenna is 41.5 dB. Then I have gain of the satellite antenna is 32 dB on axis. And off axis is 3 dB. So this is edge beam loss. Remember, this is the correction for the particular terminal not being in the main beam of the antenna, but being on a minus 3 dB contour relative to the main beam. The free space loss at KU band is 27.1 dB. So this is free space. The noise bandwidth is 30 megahertz. And the temperature of the transponder is 500 K. Loss of the atmospheric losses are 1 dB. Right? So what is the power that I need to have on a transmission if I were to use this in a TDMA mode? This is a very good example for an exam. Right? It kind of combines these few a couple of last chapters that we've been covering. So the first step, let me calculate noise on the uplink. How large is the noise? The noise is 10 log of K times the T transponder times the noise bandwidth of the transponder. How much is the noise floor on the transponder? And if you calculate this, in this case, this is 10 log of 1.38 times 10 to the minus 23 joule per Kelvin times, what did I say, 500 Kelvin, and times 30 times 10 to the 6 hertz. So this gives me a noise floor of minus 126.8 dB watt. So that's where the power of the noise is at the transponder across the entire transponder, right? Because we in the TDMA mode, you're using the entire transponder. So the total power within this 30 megahertz of the noise bandwidth is minus 127 dB watts, right? That's what enters in terms of the noise. If I have the C to N of 20 dB, then I can calculate C. C on the uplink is going to be noise on the uplink plus C to N on the uplink. So in our case, this is minus 126.8 dB watt plus 20 dB. And this is minus 106.8 dB watt. So that's the power of the carrier that I need to provide from the ground to the transponder, right? Across all of these link budget losses that I have listed here. So if I look at the C on the uplink, is going to be your transmitted conductive power of the earth station, what you deliver to the antenna, plus the gain of the earth station, minus the free space loss, minus the off-beam loss, minus the atmospheric losses, and then plus the gain of the satellite antenna, right? This gives me the C, right? It's just going through the link budget. So from here, I have everything. I have C of the uplink. I have all of these gains and losses, and then you can easily calculate the transmit power on the uplink. Needs to be minus 106.8 dB watt, and then minus 32 for the, I guess, earth station antenna, right? Is that earth? No, this is the satellite antenna, plus the earth station antenna, minus the off-beam, minus atmospheric, and minus 27.1 everything in dB. And when you calculate this, this ends up being 30.78 dB watt, which is 1120 watts. So you need a 1 kilowatt, in excess of 1 kilowatt of PRP to transmit 64 kilobits per second. You're going to use this channel for a very short time, right? You're just going to burst a very short burst, but when you're bursting it, it needs to be very powerful. So you have to have an earth station that is capable of transmitting a high ERP, but for a very short time. Now let's compare this against FDMA. In this case, your bit rate is 64 kilobits per second. Now, if you're using QPSK, what's your symbol rate?
64 times 2.
64 times 2?
UPSK times 4.
Times 4?
Divided by
Divided by?
By 2.
By 2.
2, yes.
Divided by 2, 64 kilobits per second, 2 bits per symbol, right, in QPSK. So you have 32 kilosymbols per second. So symbol rate is 32 kilosymbols per second. I use symbols here so that it is consistent with other classes we teach. Sometimes you would hear the term baud, right? Baud or symbol, right? So there is, you can say 32 kilobauds or bauds per second, meaning 32 kilosymbols per second, right? Symbol. So now, what did we say about your bandwidth? The bandwidth is going to be, the noise bandwidth is going to be around 32 kilohertz as well. Your bandwidth is proportional to your symbol rate, right? Just slightly larger than the symbol rate by little bit, right? So to transmit this kind of bit rate through QPSK modulation scheme, you need around 32 kilohertz of spectrum to fit that comfortably, right? A little bit, maybe a little bit more than that, but around 32 kilobits per second. So now, if I calculate noise on the uplink, in this case becomes 10 log of K times T of the transponder times the noise bandwidth, and this is 10 log 1.38 times 10 to the minus 23 times 500 times 32 times 10 to the 3 hertz. This is in Kelvin. This gives you the noise bandwidth, the noise power of minus 156 dB watt. If I assume the same C to N, because I'm using the same modulation scheme, then I need that the C on the uplink needs to be 20 dBs above this, so it's going to be neg 136.56 dB watt. Right? So now, if you look at what was it before, it was neg 106.8. Now it's neg 136.56, so it's significantly lower. And if you go back and you calculate the conductive power, it's going to be around 0.44 dB watt, which is around 1.1 watt. So look at the difference. The difference is now, okay, if you operate these kind of satellite terminals in FDMA mode, because each one of them is now operating over a smaller portion of the spectrum, it will transmit much longer. As a matter of fact, it will hold this portion of the spectrum for the duration of the transmission, but it will require far less of a power to close the link. And a lot of times, that's your chief constraint, how much power you can deliver. If these BSET terminals are something that you have soldier carry on their back, or something that's on the top of the vehicle, or something that's on the top of the airplane, or sitting on the side of the house, then you cannot really furnish this much of a power, right? It has to be something that is comparable to more than this. And that's why a lot of systems still operate, satellite systems still operate FDMA, right? Because it allows them to scale their power relative to the portion of the bandwidth that they're using. Remember last time we talked about it as well. The key is the power spectral density. And then if you're using a smaller portion of the bandwidth, then your power scale is appropriate as well. Right? So that's TDMA. Next time we're going to talk about the third access scheme that we find. That's a CDMA access scheme. And then we'll do some problems and close the semester.